Hello guys, welcome back to my channel Gamma Die Gamma. So in the last video, if I'm not wrong, we basically discussed operators in the general curvilinear system. So in this video, let's apply those concepts, those basic ideas that were expressed as formulae. Because only when we do specific examples, specific curvilinear systems such as the cylindrical system, the spherical system, and etc., that's when you're actually going to learn a lot. So let's dive in to all these things. So for the cylindrical system, we have variables rho, phi, and z. And if you have some point, say this is the origin, some point q, well, the distance of that point from the origin is what is denoted by this rho. The angle that, well, the projection of this guy onto the xy plane, that projection, what angle that guy subtends with respect to the x-axis is the parameter rho, and z is, well, just like the z-axis in your Cartesian system. So it's basically the distance along the z-axis of this guy, point q. Okay, so I hope this picture is clear. And then the conversions from Cartesian to cylindrical is x is rho cosine phi. You could clearly see this from the trigonometry in the xy plane. Y is rho sine phi, and z is just z. So it's not that bad. You know, if z is 1, if you fix z, you just get the polar system, the polar coordinate system. I won't do that because that's like a special case of this. And now we can define our position vector as x e1 hat, y e2 hat, z e3 hat. This is the position vector of point xyz in the Cartesian system. Now we can represent the same using these guys. So we have rho cosine phi e1 hat plus rho sine phi e2 hat plus z e3 hat. And if we want to find basis vectors in this new cylindrical system, remember this formula from last video: partial derivative of r with respect to, say, qi times 1 over hi, where hi, the scaling factor, was the magnitude of partial derivative of the position vector with respect to that free variable. Okay, so we can find h rho, which will be the magnitude of this. Well, we can find we have r expressed where each x, y, and z are expressed in the cylindrical system, so we can differentiate with respect to this rho. We just get cosine phi e1 hat plus sine phi e2 hat, and this is just 0, e3 hat. Well, the magnitude of this vector is just simple. Just take the square root, component squared plus component squared plus third component squared, and this by trigonometry turns out to be 1. Now we can do, well, instead of just jumping on ahead, we can see that q sub rho hat is just this guy divided by its magnitude, the vector inside divided by its magnitude. The magnitude is 1, so it's just the vector inside, which is cosine phi e1 hat plus sine phi E2 hat, and you forget this last guy. So that's the row basis vector expressed as a linear combination of the standard basis vectors. Now what we can do is we can find partial r with respect to phi. Well, differentiate this, we get negative rho sine phi E1 plus rho cosine phi E2, and then again we have a 0 E3. For the scaling factor h sub phi, we have just the magnitude of this, so that's going to be square root of negative rho sine phi squared plus rho cosine phi squared plus 0 squared. All of this just turns out to be rho. Now to find the basis vector q sub psi hat, q sub phi hat. I'm really sorry for messing up my Greek letters. Okay, so what we do is we have this guy. You just divide this by rho according to this formula here. Basically normalize this partial derivative operation. So you just get negative sine phi E1 plus cosine phi E2. For the z is actually the easiest one out of these guys. You do that, you just end up with E3 hat, whose magnitude is, you don't even need to do anything, is 1. So q sub z hat is just E3. So the Cartesian basis vector is the same as the z basis vector in the cylindrical system. This just proves the fact. Okay, now what do? We have like bunch of conversions. We have q sub rho hat expressed in as a linear combination of standard basis vectors, and same thing with q sub phi hat and q sub z hat. What we can do is we can write this as a column vector. So you get q sub rho hat, q sub phi hat, q sub z hat, and then I can have a matrix here, and then E1 hat, E2 hat, E3 hat. If you observe closely, noticing what linear combination is going on, you'll notice the first guy here is cosine phi, then you have a sine phi and a 0, you have a negative sine phi, cosine phi, 0, and then last 0 0 1 in the last row. And if you call this guy, say T for transformation matrix that transforms your Cartesian basis vectors into your cylindrical basis vectors. So it's just like a function, a linear transformation to be precise. So you see how linear algebra comes in finally. It's all beautiful the way these things are connected, you know, this partial differentiation and then this linear algebra, this introduction of this linear transformation from one basis to another basis. One interesting thing to notice, this matrix T, well, if you have, say, T transpose times T, if you do this, well, let me just write that out. Cosine phi negative sine phi 0, sine phi cosine phi 0, 0 0 1, multiplied with cosine phi sine phi 0, negative sine phi cosine phi 0, 0 0 1. If you do this multiplication meticulously, you just end up with the identity matrix, 3 by 3 identity matrix. And you'll get the same if you have, say, T times T transpose. So this means that T transpose is nothing but T inverse. So such matrices that satisfy T transpose T is equal to T transpose is equal to the identity, such real matrices that satisfy this are called orthogonal matrices. Well, the matrices have to be real. If they're not, we won't have a transpose, we will have a Hermitian, and in that case the matrices will be unitary matrices. Okay, so this is a nice thing, and it clearly this ties in with the fact that I remember our system was orthonormal. All for this entire derivation, entire last video and the video before that was all on the understanding that these systems are orthonormal. So this shouldn't be a surprise that the matrices are orthogonal or the transposes are the inverses. So it's all neatly connected, it's all interlinked with each other, these facts. Okay, now what does the differential volume element look like? I can draw a quick diagram, which may not be the best diagram ever, but okay. So if you have, this is say d rho, subtend some angle, call that d phi, and this angle is small so that this curvature, this arc length curvature is pretty much a straight line, and then the height that this entire thing subtends is dz. So this looks like some sort of wedge, some slice of cheese, but you see clearly it's I mean, we didn't have to show this as a straight line, we could have also shown a little curvature here, but in any case, you know what, I think let's just show a curvature, although it'll kind of be like a straight line, but so you see this curve here. That's why it is like the curvilinear system, and that's why we showed curves for the most general case in the differential volume element in last video. Okay, and so d tau, if you remember the formula, is all the scaling factors times all the free variable d's of all the free variables. So the only scaling factor is rho, that is not 1. Well, the rho scaling factor is 1, the phi scaling factor is rho, and the z scaling factor is 1. So we just have one rho out here, and d rho, d phi, dz. Yes, you can see this by geometry in this case, because, well, you have, for this slice, you have this length and this length, so you just multiply them, but you also need this length, you need the arc length. So for the arc length we have the radius times the angle, so that will be rho times d phi. So you get that relationship going down there. Well, what is the gradient of, say, big phi in this system is, if you remember the formula, 1 over hi partial big phi over partial qi hat. So we'll have to write this as a vector. So we have partial phi with respect to rho, scaling factor is 1, q sub rho hat plus, now the scaling factor is rho here, partial big phi with respect to small phi, q sub small phi hat, plus scaling factor is 1 again, so partial phi with respect to z, q sub z hat. Okay, what is the divergence of some vector field A in this system? If you remember correctly, the formula for the divergence of 1 over h1 h2 h3 partial h2 h3 a1 partial q1 plus partial h1 h3 a2 partial q2 plus partial h1 h2 a3 partial q3. So all we do is just have this 1 over rho, just fill everything in, partial rho a sub rho. So this is the rhoth component of vector field A, partial rho partial a sub phi with respect to phi plus partial rho a sub z with respect to z. Now one thing that you can do is pull the rho out of this this last derivative term, because we're clearly differentiating with respect to z. You can't do this for the first term because we are differentiating with respect to rho, and there's a rho. You cannot pull the components of A out, because we don't know if they might depend on rho, phi or z. So we can just simplify it one way. So this just becomes 1 over rho partial rho a sub rho with respect to rho, too many rows there, 1 over rho partial a sub phi with respect to phi plus the rows cancel out, partial a sub z with respect to z. So that is the divergence of a vector field A in this system. So what you do is you express vector field A in this new system, and then you plug for all these guys, because so you have to expand A in the cylindrical system, then you can plug in these values nicely. Okay, what about the curl vector field A? Remember the formula is 1 over h1 h2 h3 h1 q1 hat h2 q2 hat h3 q3 hat partial with respect to q1 partial with respect to q2 partial with respect to q3 h1 a1 h2 a2 h3 a3, and we're taking the determinant of this guy. So just substitute everything in. Q sub rho hat, rho q sub phi hat, q sub z hat, partial with respect to rho, partial with respect to phi, partial with respect to z, a sub rho, rho, a sub phi, a sub z. Take the determinant of this guy. So I'm gonna skip all those big ass calculations. 1 over rho, and the first term is partial with respect to phi, a sub z, minus rho, partial with respect to z, a sub phi. The rho was actually inside, but I took it out. I'm skipping steps here. Q sub rho hat minus partial with respect to rho a sub z, partial with respect to z a sub rho, Q sub phi hat 1 over rho partial with respect to rho, rho a sub phi minus partial with respect to phi a sub rho q sub z hat. So this big ass expression is for the curl of A. So we have, I think, derived all the, or discussed all the things that were necessary to discuss in the cylindrical system. Let's move on to the next system now. Okay, for the spherical system we have free variables rho, phi. Let me correct this. Let's be particular about it. Rho, theta, and phi. This is obeying again the right hand convention, the right hand order. because we don't want like negatives in the cross product popping in because the system wasn't right-handed. Okay, so assuming you have some point here, point Q, this is the origin O. Again, the sort of the radial distance, this point from the origin is what is rho. If you project this guy onto, say, this plane, the XY plane, this is your x-axis, this is your y-axis, this is your z-axis, then this angle, it subtends from the x-axis, is phi. Well, the angle it subtends from the z-axis now is theta. So I hope you see the picture. It's hard to visualize 3D sometimes. I hope you see it. Now the conversions are x is rho sine theta cosine phi. You can clearly do the geometry. First project this onto xy plane and then project that projection onto the x-axis to get the x component. Project that projection onto the y-axis to get the y component. And you don't need to project it onto the xy plane, just project onto the z-axis to get the z component. So you get this. Now the position vector can be written as simple: rho sine theta cosine phi e1 hat plus rho sine theta sine phi e2 hat plus rho cosine theta e3 hat. Okay, now we can find partial position vector with respect to the first free variable rho. You just get sine theta cosine phi e1 hat plus sine theta sine phi e2 hat plus cosine theta e3 hat. Just take the magnitude of this guy for the scaling factor, h sub rho, and you do that, you simply get 1. I'm just skipping some steps here. Q sub rho hat is now this guy divided by the scaling factor, which is 1. So it's just sine theta cosine phi e1 hat plus sine theta sine phi e2 hat plus cosine theta e3 hat. Fair enough. Let's move on. Partial r with respect to theta is rho cosine theta cosine phi e1 hat. I'm just differentiating this with respect to theta now. Rho cosine theta sine phi e2 hat negative rho sine theta e3 hat. So h sub theta is just the magnitude of this guy. If you do, so if you take the square root and take the magnitude, rho squared cosine squared theta cosine squared phi, rho squared cosine squared theta sine squared phi, rho squared sine squared theta. If you do all of this bad calculation, you get just rho. Okay, so q sub theta hat is divide out the rho, cosine theta cosine phi e1 plus cosine theta sine phi e2 hat negative sine theta e3 hat. Okay, now the last guy, partial r with respect to phi. If you do that, you have negative rho sine theta sine phi e1 hat negative rho cosine theta, I'm sorry, sine theta, I think you'll have a plus here, cosine phi e2 hat, and you have a 0 e3 hat because there's no phi for that. So h sub phi is the magnitude of this partial derivative calculation, which, let's do this, rho squared sine squared theta sine squared phi, rho squared sine squared theta cosine squared phi is just rho sine theta. Yes, it's a little non-trivial this time. Okay, so q sub phi hat is just divide out this guy from the top expression. So if negative sine phi e1 hat plus cosine phi e2 hat plus 0 e3 hat. Okay, now convert this all of our results into a matrix. So this becomes sine theta cosine phi, sine theta sine phi, cosine theta cosine phi, cosine theta sine phi, negative sine theta, negative sine phi, cosine phi, and 0. E1 hat, E2 hat, E3 hat. So this again, calling this matrix T, is sort of the function that helps us change the basis, the Cartesian basis, to a spherical basis in this case. And again, it is orthogonal, as you might have suspected, because the entire coordinate system is orthonormal. Not just because, I mean, normality is a special luxury, but more importantly, it's the system is orthogonal. So the matrix is 2. So that's why inverting this guy is simple. So if you want to convert from say this system, spherical system, to your Cartesian systems, basically inverse of this guy, you multiply both sides by the inverse. By definition, the inverse will just give the identity here. But the inverse is just the transpose, because the matrix is orthogonal, as discussed here. So it's easy to switch from, have a different transformation going on, even the inverse transformation in this case. Okay, now what does the differential volume element look like? Okay, let me try my best. So this is d rho. If you subtend some angle d phi, and then this angle, sort of like your d theta. Okay, this is my best. I'm sorry if this didn't really make sense to you, but so you see this like bulge on this guy. That's because there's like two angle dependencies. This first curvature is because of the phi angle, and then this like upward going curvature, sort of like lines of longitudes converging. I mean, it kind of makes sense to call them longitudes because we're in a spherical system. I think this is the best I can do. And d tau is, multiply all the scaling factors. For rho, scaling factor was 1. For theta, scaling factor was rho. For phi, scaling factor was again rho sine theta. So rho squared sine theta d rho d theta d phi. that is your volume element. And if you integrate this on, you know, appropriate upper and lower bounds and set, say, rho equal to 1 or even rho equal to some magnitude, you can get the volume of a sphere of that radius, of that rho value. But it will be a triple integral definitely, because you see these three differential terms. Okay, let's move on to the other differential operators now. So moving on to the gradient, some scalar fields, capital phi. This just becomes, I'm going to skip some steps. d phi with respect to rho, which has scaling factor 1, so don't divide by anything. Q sub rho plus 1 over rho partial phi with respect to theta, Q sub theta, 1 over rho sine theta partial phi, big phi with respect to small phi, Q sub phi. Okay, let's do the divergence vector field A. Well, I'm gonna skip some steps, but you just use the formula and then you get partial rho squared A sub rho 1 over rho sine theta partial sub theta sine theta A sub theta plus partial with respect to rho partial with respect to phi 1 over rho sine theta A sub phi. Okay, so the last guy is, well, the curl of A. And again, I'm gonna skip some steps. We have 1 over rho squared sine theta Q sub rho hat rho Q sub theta hat rho sine theta Q sub phi hat partial with respect to rho, partial with respect to theta, partial with respect to phi. A sub rho A sub theta, rho sine theta A sub phi. Skipping all the steps, 1 over rho sine theta partial sine theta A sub phi respect to theta minus partial A sub theta with respect to phi Q sub rho hat 1 over rho 1 over sine theta partial A sub rho with respect to phi minus partial rho A sub phi with respect to rho Q sub theta hat 1 over rho partial rho A sub theta with respect to rho minus partial A sub rho with respect to theta Q sub phi hat. Wow, too many Greek alphabets. If you want, I can do the Laplacian of A. Okay, so let's do this quickly. The Laplacian is the divergence of the curl, divergence of the gradient of a scalar field. Let's do the scalar one before, which is the Laplacian. So for that, you just need to substitute the gradient term inside this formula. Instead of say a sub rho, substitute this guy, the first component, the rho component. So partial with respect to rho squared times this guy, rho squared times partial phi with respect to rho. Okay, plus, since the divergence we don't really care about, those vector terms. For this guy now, we have 1 over rho sine theta, and then 1 over rho times d phi with respect to theta, so the rho comes out. So we have 1 over rho squared sine theta partial with respect to theta sine theta partial phi with respect to theta, plus the last term. So we have this term that's repeated, so rho squared sine squared theta, and this guy 1 over rho squared sine squared theta partial with respect to phi partial, I'm sorry, this small phi, capital phi with respect to small phi. So this becomes a second partial derivative. So this is the Laplacian in the spherical system, and it becomes a matter of importance later on when you're studying partial differential equations to show that the Laplace's equation is has a rotational symmetry. It becomes a matter of convenience, importance later on, because that's how you solve it. An elegant way is to basically convert it into write Laplace's equation in the spherical system and then show that it's angle independent. So that's rotational symmetry. Okay, so this last coordinate system is sort of a surprise. This is not really one of those coordinate systems that is covered in like a basic engineering class or basic mathematical physics class, but it was important. It was nice. It's important in terms of solid state physics. More than solid state, I would say high energy physics, because when you have tokamaks, they are usually in toroidal containment units. So the TO is for the toroidal in that acronym. Okay, so the parameters we have are theta and phi again, but there's a slight difference. We are working with toroids, and toroids are sort of like donuts. This is, say, 1/2 cross section of that donut, that torus. We have one fixed value. It's called the radius, r0, the capital radius. From this origin to the center of this circle, that's fixed. And then assuming you have some point here, I don't know, call that Q. Well, we can define like a radius parameter, that's a variable. So this is r, so the radial distance from this point to any point that's extending outward on the surface of this donut. And then we have this theta parameter, and then we have also a phi parameter. So for this guy, for example, so it was kind of hard to show the theta you can see, so this for example is like r, theta is sort of this guy, and the other guy is the phi. So the angle you subtend with the x-axis as you go along this this donut. Okay, so if you notice by geometry, x is basically r naught minus r cosine theta, so that will be just the projection onto the xy plane, and you project that onto the x-axis. So cosine phi, y is r naught minus r cosine theta sine phi, z is just r sine theta, because there is no r naught dependence now, you just project it onto the z-axis directly. I'm sorry, this is the z-axis. Okay, again, define the position vector because we need to differentiate that. So r naught minus r cosine theta cosine phi e1 hat plus r naught minus r cosine theta sine phi e2 hat plus r sine theta e3 hat. And we can define partial r with respect to parameter r is just let's see, negative cosine theta cosine phi e1 hat, negative cosine theta sine phi e2 hat plus sine theta e3 hat. H sub r scaling factor is just going to be 1, just like in the case of the spherical system. Partial position vector with respect to theta is r sine theta cosine phi e1 hat, r sine theta sine phi e2 hat, and I believe here we have a r cosine theta e3 hat. H sub theta is going to be r. Partial position vector with respect to phi is going to be negative r naught minus r cosine theta sine phi e sub 1 hat plus r naught minus r cosine theta cosine phi e2 hat, and we have a 0 e3 hat. So h sub phi, which is the magnitude of this guy, is surprisingly r naught minus r cosine theta. I forgot to define q sub r, which will just be cosine theta cosine phi e1 hat negative cosine theta sine phi e2 hat plus sine theta e3 hat, and also q sub theta, just eliminate the r, sine theta cosine phi e1 hat sine theta sine phi e2 hat cosine theta e3 hat. Q sub phi hat is negative sine phi e1 hat plus cosine phi e2 hat. Okay, we can write this in a vector, column vector form. So the matrix is going to be negative cosine theta cosine phi, negative cosine theta sine phi, in case you're wondering how I get this, is you can check by, using matrix multiplication that you actually get those values. Again, if you watch my linear algebra playlist, you'll understand this concept way more. We have cosine theta here, negative sine phi, cosine phi, and a 0, e1 hat, e2 hat, e3 hat, and that is your complete matrix. This helps us to transform from one system to another, and you'll see when we go forward, when we do more tensors, you'll see how important these guys are, the transformation matrices, covariance, contravariance, and all that. And again, this is orthogonal because the coordinate system was designed to be orthogonal. At least the way we have these quantities defined. As long as you can express each basis vector as a linear combination of Cartesian basis vectors, you have hope you can convert that into an orthogonal system by using this process and then normalizing it out. Okay, I hope you like this video. I won't draw a differential slice for this because it's gonna be a little weird. It's gonna be super weird. You know what? Let me just try that. Let me just. So this is dr. D theta is. Sorry, okay, yeah. This is r. This is basically at point r0 from the origin. It's dr. D theta is gonna be, say, something like this. And then d phi sort of gonna be, it's gonna like trace behind, it's gonna, yes, something like that. I hope you see this. I hope this makes sense in any way, because d tau is nothing but 1 times r times r0 minus r cosine theta dr d theta d phi. If we integrate this, we can get the volume of a torus. So you see how convenient this is. Again, I said it's relevant in high energy physics because you have magnetic field lines that are sort of going out like this. You sustain a nuclear fusion reaction inside something like this, a toroidal containment chamber which has magnetic field lines like that. So the magnetic field lines, of course, they get more complicated. I've seen some math in some research papers. It's really messed up. It's crazy math. But you have a toroidal system. It makes everything easier to work with. Okay. So I think this is it for this video. This is where we should stop. So please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Di Gamma. In the meantime, stay home, stay safe, keep doing math, and stay tuned for more content. Peace out.